Okay, so for the sake of time and frankly redundancy going through the process, I'm going to, for this video series, sort of cut off at the tangent inverse, and at the beginning of class we'll kick off with the cosecant inverse, the secant inverse, and the cotangent inverse. But the long story short is what we've been noticing as we've been going through the process of finding these derivatives is that even though we have derivatives stated in terms of inverse trig functions, we can rewrite in terms of the original trig functions and use our implicit derivative technique to be able to find the derivative of our original function. So let's work through the problem of finding the derivative of the inverse tangent function. And like we did in the previous two cases, we first wish that we weren't in terms of the inverse trig function because we don't know the derivative of the inverse trig function. Well, that's fine, because if the inverse trig function is taking us from this ratio to that angle, then the standard trig function would take us from that angle to that ratio. And as soon as we're written in this form, we now have something that's implicit, but we can take the derivative of something implicitly. Yes, this is not in the form y equals anymore, but even though we're not in the term form y equals, we use our implicit derivative technique, which is take the derivative of the left-hand side. You know the derivative of tangent y, that's just secant squared y. Tack on a dy because you took a derivative with respect to y. You know the derivative of x, that's just 1. Tack on a dx because you took the derivative with respect to x. Now, get all the dy terms on one side, all the dx terms on the other. Actually, that's already done for us by convenience here. So now, we want to get dy over dx. Let's isolate our dy by dividing by secant squared. So divide both sides by secant squared. We get 1 over secant squared times our dx that we originally tacked on. And now we don't want just dy, we want dy divided by dx, so we can get that by dividing both sides by dx, and we'll get dy over dx equals 1 over secant squared, whoops, I made a mistake here, 1 over secant squared y. And we wish we could just write the answer as 1 over secant squared y, but we can't because you see our original function was in terms of x, and this statement is in terms of y. So our goal is to get our derivative expression where the expression here only depends on x. And since our expression that resulted depended on y, and we want something that depends on x, we need an expression that relates y and x. And we've got that right here. Here is a relation between y and x. The tangent of angle y is x. Now, even whenever I say that, tangent of y is x, tangent, you know, is opposite over adjacent. So it would be nice if we had that x written as a fraction. Let's write it as x over 1. Like tangent always is opposite over adjacent. So let us go to a triangle. Let us plop in our angle y, and let us write our opposite over our adjacent as x and 1. Now, we want to find the secant, in particular the secant squared. Well, if we find the secant, we just multiply it by itself, we'll have the secant squared. But to find the secant, what do we need? The secant is the hypotenuse over the adjacent. So we need to find this missing hypotenuse side. What is that hypotenuse going to be? Well, we know two sides. You can always find the third using Pythagoras. So in this case, that would be 1 squared plus x squared equals the hypotenuse squared. We want to know the hypotenuse, so let's take the square root of both sides. The square root is 1 plus x squared. I've simplified 1 squared as 1 because we know that 1 times 1 is just itself. But the hypotenuse is just square root of 1 plus x squared. No sweat. Now, this allows us to find the secant. The secant, as it always is, hypotenuse over adjacent. This is square root 1 plus x squared over 1. But now we don't want the secant, we want the secant squared. So that is not too hard to find because all we've got to do is square both sides. So if we multiply the left side by itself, we get secant times secant, which is secant squared. If we multiply the right side by itself, I mean, hell, anything divided by 1 is just itself, and the square root times itself will give you what's inside. So the secant squared is 1 plus x squared. We were looking for something that depended only on x, and now we have that something because we know that secant squared is 1 plus x squared, so we can take that secant squared and plug in, and we get the derivative of our tan inverse to be 1 over 1 plus x squared. And now we are one formula closer to having all 6 inverse trig functions. 3 left to go. We'll start class there to sort of familiarize ourselves with this process. But heck, we've got a great start on now having derivatives of our inverse trig functions. We're halfway home.